Well, I hope we have continuity here on the Camtasia. Somehow this connector seems to get more flaky every day. I'd like to make a few comments about offset voltages. We started last time, and then we'll move into common feedback circuits. As we pointed out last time, the offset voltage is comprised of two parts: a systematic part and a random part. Systematic part is the part the designer intentionally leaves in the design. The random part is comprised of two components, one due to local random variations and one due to gradient effects. And we talked about the local random variation effects last time. Local random variations effects are the things that have changes in the properties in very, very short distances that are a small fraction of the dimensions of a transistor. Gradient effects are those effects that occur over long distances that are comparable to the layout of a input stage of an amplifier. We saw that both effects are basically Gaussian if you look at the offset voltage distributions. We then looked at two structures. I only spent time with one, but here are two different structures. One is a single-ended output structure where we have a current mirror load on the top, and one is a single-ended, is what can be a differential output structure where we have a common feedback circuit to generate the voltage Vx. And you can show that in either case, the offset voltage can be expressed as a function of device dimensions and model parameters, and these are matching model parameters, and they're oftentimes called the Peldrome parameters because Gallaudet and Peldrome published a paper using this terminology, and it's been pretty much been adopted by the industry. He's not the first guy to observe the effect, but he did a fantastic job of systematically describing the effect and presenting a lot of experimental data to support his claims. Ironically, he's not quite right. But even though he's not quite right, the ideas are still used all the time. There's a correlation between the random variables he ignored, and a few years later, a group at Motorola at the time, McAndrew and Drennan, pointed out that Peldrome missed some correlation in his parameters. So anyway, this somewhat complicated expression oftentimes simplifies to this expression here. The standard deviation of the offset, or the variance of the offset, is twice AVT0n squared over the area of the n-channel devices plus mu p over mu n times ln over l times 1 over times ln over lp times the maybe we put WP in here and show it in terms of the area of the p-channel devices times a squared of VT0p. And then we can calculate, and we get the same expression for both structures, whether we have a current mirror load or whether we have a differential output structure. And we see that the way to drive this down is to increase the area of the devices. We saw a similar expression for bipolar structures, and it applies to both the differential output, single-ended output, and the differential output structures. Again, there are two matching parameters, HA and HAP for the NP and the PNP transistors respectively. And down here we have the area of the emitter and of the N-channel and the area of the emitter of the P-channel. If you look at typical offset voltages for comparable sized devices, MOS devices typically have a much higher offset voltage than BJT devices. And unfortunately, that's an undesirable characteristic of MOS transistors. It's difficult to justify putting enough area in a MOS structure to get the offset voltage really low. we oftentimes have to go to a circuit that will take the offset voltage out by adding additional circuitry. I'd like to talk about common centroid layouts because we said there were two effects that contributed to the offset voltage of an operational amplifier. One was the gradient effects and one was the random local variation. So now we'll try to address the gradient effects. Before I do that, I'd like to talk about a common centroid layout. If we let P be a process parameter that varies with position in the channel region, so this could be the threshold voltage, it could be the mobility, it could be COX, and so forth. Here's what we call an almost theorem. If P of X and Y varies throughout a two-dimensional region, then the equivalent value of that parameter, and the equivalent value is the parameter we're going to put in our square law model of our device, it's equal to 1 over the area times the integral of that parameter as a function of position x and y dx dy, and you integrate that over the area. So this relationship applies to threshold voltage, mobility, COX, and a few other parameters, although these are the major ones we're concerned about when we look at matching. So this could be a region. I don't see a transistor yet. This could be a region. And we might ask the question, what's the effective threshold voltage of that region? So the threshold voltage will vary with position in that region. And it just says we have to integrate the threshold voltage then across that region and divide by the area. Here's another almost theorem. And the reason I call these almost theorems, we hinted about that last time. Why do I call them almost theorems? Why do I call them almost theorems instead of calling them theorems? Garrett?
We like to show that they're obviously wrong.
They're wrong. But they're a good approximation for most circuits. Okay? So here's another almost theorem. If P of X and Y varies linearly throughout a two-dimensional region, so now we're not looking at local random variation, we're looking at a linear effect, then the equivalent value of that parameter is equal to that value of that parameter at the geometric centroid of the region. So you can go through the whole region and have a linear variation. If it's a linear variation, we call it a linear gradient. Makes no difference what the direction is to the gradient. To find the equivalent value of that parameter, you just have to find the geometric centroid and find the value of that parameter to the centroid, and that will be the equivalent value of that parameter. It'll be the same thing you get if you integrate over that region, that parameter, then divide by the area. It's not surprising maybe, because that's how you use the same kind of integral to find the geometric centroid. Okay? So if a parameter varies linearly throughout a two-dimensional region, we say it has a linear gradient. Many parameters have a dominantly linear gradient over rather small regions. And the reason they have a relatively linear gradient, and we gave an analogy of the topography of the United States last time, things change kind of slowly if you somewhat linearly if you are looking over a relatively small region. Looking out the window here at the street, or it might be a little bit of slope, so the water runs off, but it's kind of a smooth gradient. If you drive around the city, you see all the lots hopefully are graded so that they drain to the streets that go down the greens. Each one has a different slope probably. In fact, the front of your lot and your back of your lot have different slopes, but there's a relatively smooth slope in a given region. So there's a picture of what's going on then. If we have an arbitrary shaped region, and x0, y0 is the geometric centroid, then the equivalent value of that parameter, if it varies linearly throughout that region in any direction, is simply the value of that parameter at that geometric centroid. Okay. It's not affected by the direction. It's not affected by the magnitude of the gradient. Like to recall that if you have a transistor with 2W and length L, that's essentially equivalent to 2 transistors in parallel, each of width W and length L. Or if you have N transistors of width W, that's equivalent to a single transistor of width K times W. Let's now talk about common centroids or centroids of segmented geometries. You know, if you look at that almost theorem, the almost theorem did not have a statement that the region had to be a contiguous region. It just said that if you have a linear gradient, then the value of that corresponding parameter's equivalent value is the value at the geometric centroid. So here you could look at it as 2 regions. These 2 regions, think of as a single region, and the geometric centroid of these 2 regions happens to be here. The geometric centroid is not interior to either of the regions, but it's outside the 2 regions. Here are 2 other regions, and here happens to be the geometric centroid of these 2 regions. So for any geometry, we can, whether we have a single contiguous region or several separate regions, we can determine the geometric centroid. If you look at these green and gold regions here on the top, notice that both have a centroid at the place where the X is marked. So we would say that these 2 regions, the green region and the gold region, have a common centroid. The centroid of the gold and the centroid of the greens are the same. Likewise on the bottom, the centroids of the golds and the centroids of the greens are the same. So we would say they have a common centroid. Areas don't have to be the same. So here the gold and the greens have the same, but one has a bigger area than the other one. On the bottom, we have 4 different regions. All 4 regions have a common centroid. Okay. If there's a linear gradient in the threshold voltage, even if the regions are not connected, if you look at the way the threshold voltage varies, that variation, that linear variation, will continue across regions even where the active is missing. Okay, so it would not be uncommon to have a threshold voltage variation of several, in the lowercase 8 separate regions, where the gradient would be as if it was one contiguous region. Common centroid layouts are widely, almost always used when matching of devices or components, because these layouts will cancel all first order gradient effects. I wonder why they cancel gradient effects. If you have 2 devices and the equivalent threshold voltages are different, the devices won't match, right? If you have M1 and M2 and they have different threshold voltages, then the currents won't match. If they have the same threshold voltage, then ideally they'll match. So if we have a common centroid layout, then their threshold voltage for both devices will be the value you get at that centroid, and it'll still be the same, and hence they'll match. Okay. So common centroid layouts are widely used, almost always used when matching of device or components is critical, because these layouts will cancel all first order gradients. This applies to resistors, capacitors, transistors, and other components. It's important to orient devices the same way. So, if you have a transistor, and if this is the drain, and this is the source in your circuit, So this might correspond to the channel of M1. And this might correspond to the channel of M2. Then we say these are oriented the same way. If current flows from drain to source, it flows down in both cases. I could easily use the same layout and make this the drain and this the source of M1, and make this the drain and this the source of M2. And now if you look at current flowing from drain to source, it's going to flow vertically in this direction here, and it's going to go flow up in this direction here. We've got current flowing in different directions. And we will find that even though those channel areas are drawn the same, and even though they're ideally the same, the devices will probably not match very well. Okay, so that's what it says. Always orient devices in the same way. Here's another way we can do a layout. Here is M1, the drain and the source, and here is M1 or M2, the drain and the source. Again, these are different orientations. We won't get good matching on the devices. So always orient devices in the same way. Now, got to qualify that. You might have a device that you break into 4 segments in parallel. So you want to, so one way, and you put that with another device with 4 segments in parallel for a common centroid layout. So one way to do it would be have all the drains on top for all of your devices for both M1 and M2. Another way to do it would be to have 2 of the drains on top and 2 of the drains on bottom for M1, 2 drains on top and 2 drains on the bottom for M2, and then those should match. Does that make sense? So we don't necessarily have to have the devices all oriented the same way. We have to have the same number oriented in the same direction if we want matching to occur. If you're doing the layout for common centroids, it's not enough to have a common centroid for the channel region. You also would like to have a common centroid for the drain region, the source region, and the interconnects. These might cause second order effects if you don't have those also common centroided. So the whole structure you'd like to be a common centroid. Often dummy devices are placed on the periphery to improve matching. So here's an example of where we're going to use common centroid to match 2 devices. And you can see we've broken those devices into a large number of segments. And you can see the centroid is right here. And what we do is we put dummy devices around the outside. The reason we put dummy devices around the outside is you'll find the device characteristics of a device are somewhat affected during processing by its neighbors. So if instead of having an identical device around the outside here, you got a big resistor or a big capacitor or just some open area, the characteristics of this transistor may be different than the characteristics of this one in here. So if you have matching critical circuits, you not only use common centroid layout, you typically surround your devices by dummy devices. They're not serving any electrical purpose. They're only provided there to help make all the devices more identical. Sometimes you'll see 2 rows of dummy devices. So there are rules of thumb in regard to how big that buffer region needs to be around the device until you allow lack of homogeneity to occur. Okay, so you'll see some layouts where they'll have 2 rows of dummy devices around the main core devices. I just want to mention in passing the issue of fingers and multipliers. I'm sure you've all looked at those in the laboratory, and they mean about the same things, but not quite the same things. If you use the term multiplier, you're looking at a number of identical devices, number being equal to multiplier factor. The philosophy is that use a multiplier, everything's going to be oriented the same way, and we'll have the same drain and source regions on both devices. This is an example of a situation where we have a multiplier of 2. This device and this device both oriented the same way, and also sources on the left here, sources, drains on the right here. This is an example of a situation where you have 2 fingers. And with multiple fingers, what you do is you share a diffuse region between the fingers. They can still be contact here. I don't show contacts. You can still contact it in between. So when you use fingers, if you can share the diffused area, the size of your layout can go down. If you want to put these 2 devices close together, put a contact here and a contact here, and you can only get them so close. You've got a spacing here that has to do with 2 contacts plus the spacing from contact to active, from the spacing from contact to active, plus the spacing from active to active. So there's a fair distance between here and here if you have separate drains and sources. If you have this layout here, you can put contacts down the middle, and you only have 1 contact spacing and 1 spacing between contact and active or poly that you have to worry about. So these can be more dense layouts. You can reduce the parasitic capacitance on this node quite a bit, and the parasitic resistance of that node quite a bit, by sharing this node between this transistor and this transistor. Okay. We have a choice of doing contacted or non-contacted regions. So here, this might be 2 transistors in series. We don't necessarily have to put contacts even in this region here. We have 2 fingers and we're sharing this region here. The source of this transistor is shared with the drain of this transistor. Yes?
Would it make sense to use the finger layout for the cascode, like the telescopic cascode, where we seem to have a lot of occurrences of 2 transistors in series to form a quarter circuit? Would we gain any benefit using it? So 1 finger device would represent 1 cascode pair, or is it arbitrary?
I think you're going to get in trouble if you look at a cascode configuration. Matching of the non-cascoder devices are critical. Matching of the cascoder transistors is less critical. So you'll have to account for getting the non-cascoder devices matched. I'm not sure that the fingered approach will make that easy to happen. Now, it doesn't mean that you can't use fingered approaches in a common center layout to get good matching. It's just critical that your overall structure has a common center, including drains and sources and so forth. So you can ratio match finger structures also if you want to. It might be the case that you've got one, if you have a transistor, you break it up into 16 parts, 8 of them might have current going up, 8 of them might have current going down. That's all right, as long as the other one that you're matching it to has 8 going up and 8 going down. Make sense? Okay, so anyway, the big difference is whether you do or don't share a diffuse region when you use fingers or multipliers. Well, here's the situation where we have flipped the device. So here's a single transistor here. We flip it around here. So we've got different orientations here between drain and source now. Again, you don't expect good matching for this layout. Turn it around is pretty good. here's one we sketched on the board a bit ago. We shift this 90 degrees. The channel regions ideally are the same, but again, the orientations are different, so you won't get matching between these devices. But if you had a device that was made up of 16 segments, and 8 of them were horizontal and 8 of them were vertical on each device, you'd still get good matching between those devices. Make sense? If you have a digital circuit, would it be acceptable to lay out a digital circuit, maybe a D flip-flop? Remember, D flip-flops are used a lot. And they might be used many million times in one circuit. So now you're in a situation where you spend a lot of effort making one great D flip-flop. You might spend days or weeks laying out that flip-flop to make it as compact as possible. Make sense? Because you're going to use it so often. Would it be a problem to orient the transistors in different ways in that D flip-flop? Probably not. In most logic circuits, matching of the devices is not critical. So you might say, I'm going to take advantage of being able to orient the device in a different way to cut down area, to cut down parasitic capacitance, because that's more important in those applications. Could I use finger devices there? Yeah, again, very much so. If you can use finger devices and cut down your parasitic resistance and parasitic capacitance and area in a digital circuit, probably you'll go for it. Common feedback. I took the easy route up to this point in time in this course. I would put a circuit up like this, and I just put a little note, 8 letters, needs common feedback circuit. Ignore it, right? So now we're going to go back and look at that little footnote. Needs a common feedback circuit. Common feedback circuit is necessary to establish or stabilize the operating point of the circuit or the op-amp. You can see the problem here. If I set the voltage VB2, that will set the tail current. The tail current is a function of VB2 and the dimensions of M9. On top here, this current here and this current here should be the same. And it's a function of the dimensions of these 2 transistors and this voltage VOXX. If it happens that the 2 currents that I'm trying to establish on top don't agree with the tail current, then I'm going to drive my output into one of the outputs in the triode region. And it's real hard on a circuit like this to establish device dimensions accurately enough and bias voltages accurately enough to see to it that we don't have the Q points drift way up or drift way down. So we need a common feedback circuit to bias this structure. And then we drew this diagram before, and the way the common feedback circuit is typically set up is we sense the voltages here that we would like to stabilize at some point, and we average them together, and we compare that to what we would like them to be, and then we take the difference between what we would like the average to be and what it really is. So we measure the average, compare it with what we want, provide a feedback signal to adjust the biasing voltage to hopefully drive the difference between the average value of those 2 voltages and what we want to arbitrarily small value, ideally to 0. We can provide this feedback circuit to either the biasing voltage on the P-channel devices or the biasing voltage on the tail. Or we could do it to both in some way. But usually we choose to do it to one or the other. Doesn't make much difference which we go to. If you look at the insertion point then, so we replace this biasing voltage source with a feedback voltage. And if you do this, if that feedback circuit has an output that goes up or down a little bit, it changes the current a lot here. It's real sensitive. The current's real sensitive to small changes in voltage VFB. So oftentimes we may argue that what we're going to do is break these transistors M3 and M4 into two parts. We're going to have one part that's maybe the small part, width's pretty small, and the other part that has most of the width present. We're going to go ahead and bias most of the circuit with a fixed voltage source. And we'll just see to it that the current here is always a little bit less than the tail current at the bottom. The sum of these two currents is a little bit less than the tail current. And then we're going to add a little bit more current in so that we can bring the total current coming here up to the tail current. So here what we've done is partition the devices. We're only going to provide the feedback signal to a portion of these devices rather than to the whole device. Make sense? Does everybody see why we're doing that? It reduces the sensitivity of the current with respect to that feedback voltage. So I described what that combo feedback circuit does, and here's a block diagram of how that works. You take your two output voltages, you go into an averager, and after you average them, you go into an amplifier, and you compare the average value to what you want. You generate a difference voltage, you amplify that voltage, and that becomes your feedback voltage. Okay, this works pretty great. If this gain is big, if this gain is infinite, then the average voltage will be what we want, and the feedback voltage will be what's needed to make that happen. We got a little bit of a problem. We're trying to build an amplifier, and we embed an op amp in an amplifier to build an amplifier. So now you might have to ask the question, do we need a combo feedback circuit in the A amplifier to, well, we don't here, because this is single-input output. So we're maybe gaining something. But we're going to see that this A amplifier is oftentimes a very simple amplifier, however. So it's comprised of two fundamental blocks, the averager and the differential amplifier. Oftentimes we will combine those together into a single block that does averaging and amplification by itself. Oh, but once we apply feedback, we have another feedback loop in our system. So now we have to worry about compensating that feedback loop if it's second order, and it's going to be typically second order. Let's go back and look at the capacitors in the circuit. This circuit has two capacitors, so how many poles should it have? Two. Unless there are capacitor loops. But I don't see any capacitor loops there. So this should have two poles, right? Now we've analyzed this circuit before with the differential excitation. And so with the differential excitation, we broke it into a left half circuit and a right half circuit, and points on the axis symmetry were the AC ground. And this was the circuit we analyzed. What I did here to get symmetry, I took this current source down here and I broke it into two. So I put half of it here and half of it here. Okay. Now it's the circuit we analyzed, and here was the difference mode gain, and here's the pole of the difference amplifier. Oh, there's only a single pole here. We had two energy storage elements, and only a single pole. Where did the other pole go? Is the pole still there? Yeah, it's still there. And we don't see it. And zero hasn't canceled it out. Good guess. but a 0 hasn't canceled it out. So where is that missing pole at? It's not a double pole. Good guess. It's not a double pole. If it was a double pole, we compensate these amplifiers. Instead of having 90-degree phase shift, we'd have 180-degree phase shift for a double pole, right? So it's not a double pole. Here's another circuit. This is the common mode circuit. And for the common mode circuit, I can also break it down the middle, since I've made it symmetric, and I can just consider half of it. And this differs from the previous circuit in the sense that the input is still the input I had before, but I'm no longer grounding the source. The source is going to be connected to ground through the output impedance of this transistor that we have on the bottom here, the biasing transistor. And we can easily analyze this circuit too, some currents of these two nodes, and I get this as the common mode gain. And if I neglect Gauss compared to GMs, I find it's got a pole also. Where's that missing pole at in a system? I found a pole here too. And this pole is not the same as the other pole I found when I did difference analysis. Have we found the missing pole? The system has two energy storage elements. It has two poles. One of the poles is not visible in the differential analysis. That was the one that was this one. And one is not visible in the common mode analysis. And that's the one we found for the difference analysis. So we found the missing pole. The analysis obscures it in the two cases. The difference mode analysis obscures the common mode pole. The common mode analysis obscures the difference mode pole. But you can't get rid of the poles. So if there's two energy storage elements and there's no capacitor loop, those poles are there. Make sense? So we found the missing pole. But if you look at this common mode analysis here, this input was the same as the input for the difference mode input. It tells nothing about the common mode feedback circuit. By the way, if you do simulation, the same thing happens. If you do a simulation and you simulate a difference mode circuit, simulate differently, simulate the common mode, you will also obscure the other pole in the simulations. They're still there. So the overall poles are the union of the common mode poles and difference mode poles of a system. Also, some amplifiers will need more than one common mode feedback circuit. We're going to look at one that needs one common mode feedback circuit. If you have a two-stage amplifier, you may need a common mode feedback circuit on a first stage and a separate one on the second stage. Some don't. Definition: the common mode offset voltage is the voltage that must be applied to the biasing node of the op-amp. I can bias it here or here. So I'm going to assume I apply it at this node to obtain the desired operating point at the stabilization node. So here's the stabilization node, DOXX is what I want. I build the circuit, and what I get here is a little bit different. So to get the right thing, I just change this voltage a little bit. That voltage is B offset, and the offset voltage, the common mode offset voltage is what's needed to get the desired quiescent point on those output nodes. Let me look at the difference mode, the common mode circuit again. You know, when I looked at the circuit initially, I assumed this was the input when I calculated the common mode gain. But if I look at the circuit, there are three voltage sources here. There are three common mode gains for the circuit. The common mode gain from the signal input to the output has no bearing on the stabilization of those output nodes. The common mode gain from the biasing nodes here and here are going to affect what that quiescent value is at the output. Because we have the ability to control those voltages on those nodes. We can't control the common mode voltage on the input nodes. So here's the common mode gain relative to the signal input. This is what we calculated before. And this is what we used in the common mode rejection ratio. Here's another common mode gain. This is the common mode gain from VC2, from this input to the output. And there's a third common mode gain from the other input to the output. How do the poles compare? Oh, is that a coincidence? No, why is it not a coincidence? Same system. Dead networks are the same. Zeros may change, but the poles don't change. The poles are fixed. They have dramatically different values. The common mode gain from the signal input, oh man, I'm out of time. I said I was going to be done with amplifiers today. When we get back on Wednesday, I will make a few additional comments about the common mode feedback circuits. You probably won't be in the common mode feedback circuits yet in the lab today if you focus on the differential singulated output structures first. Are there any questions? So a reminder, no class on Friday, no class on Monday. Homework assignment will be posted. Relatively short assignment on compensation, and then a take-home exam from Wednesday through Friday. That's all for today. Thanks.